My name is Bi Fang from Michigan State University. This is joint work with Nick, me, Aiden, and Fatim. We all know that the age of wearable is upon us. With an accelerometer-based wearable, such as Fitbit, it can track how many steps you walk every day to provide health information for you. And with microphone-based wearable, when you wear it, it can tell the difference between your drinking or your eating. And with the vision-based wearable, it can live log the amazing moment happening in front of you. And with the physiological sensor, when you wear it, it can tell you the breathing pattern or other type of vital sign. So wearable provide possibilities to understand oneself as well as the world. However, current sensor has its own limitations. Accelerometer-based wearable, they can only detect motions of the body parts where it attached to, so multiple accelerometers are needed to capture whole body movements. As for audio and video-based sensors, you will never feel comfortable if you're talking to a person who is pointing a camera towards you. And what if your audio-based wearable got stolen? Your privacy is in danger. So audio and video are privacy intrusive. And for physiological sensors, you will have to put the sensor with a firm skin contact to collect the data from your body. It is good for clinical usage, but it will never be good enough for everyday use, such as wearable. So, we need a novel sensing modality for wearable that is non-contact, privacy-preserving, while still providing rich information about users and their context. Nowadays, radio sensing has attracted considerable attention. For example, if you put a transmitter or receiver in the ambient environment, it will enable you to track whether you are sitting down or stand up, as illustrated in the figure. It can be a good application for elder care. As another example, it can help track the indoor movement with a similar setup. And if you deploy the transmitter receiver in a crowded area, it can help count how many people inside the crowd. And it's a good application, for example, for shopping center, and so on. These are very fantastic and amazing works, but when taking a closer look, they all share one single feature. All of them use Wi-Fi deployed in the ambient environment, such as homes and public places. So we kept asking ourselves, what will radio sensing mean for wearables? What if it can sense at a distance? Considering you are sitting in a cubicle, it can help you, but it can tell you that the person approaching behind you is not your boss, but just a cleaner inside the building. What if it can tell the difference? It can detect the object. It can alarm you while a stone is flying towards you, or a car is crashing you, or it can detect the material that it tells you that you are interacting with a piece of metal and plastic, which is a laptop. And secondly, can it sense a complex movement? For example, transportation mode. It will be able to detect whether you are walking, running, or taking a bus, or driving. And last but not least, can it sense a physiological signal? It tells the breathing pattern or heartbeat rate. And crazy enough, can it tell the fatigueness of your muscle? BodyScan is our first step to answer this question. It is a wearable system that uses radio to sense whole body activity and vital sign. It is able to track transportation modes such as driving and biking, hand-related activities such as typing and shaking hands, and also free weight exercises such as bicep curl and bend over row. And in addition, it can track vital sign, which is breathing rate. It solves the problem associated with the multiple sensors privacy issue, and the need of contactless, which I mentioned before. BodyScan addresses all these problems. The key principle of BodyScan is that we wear a transmitter on the wrist and a receiver on the hip with two directional antennae, one pointing to the upper body, the other to the lower body. And the movement caused by different parts of the body can cause different changes on the received signal. By analyzing these changes, the activity that caused these changes can be recognized. And we take the opportunity of static motion to detect vital sign, which is breathing in our case. Our BodyScan system architecture including three main parts. The first part is the user model. The scientific problem behind it is to study potential form factors and body locations of the sensor. The second is wearable platform. We are going to build the hardware together to investigate the system challenges and the hardware design considerations. And the third part is the radio signal processing pipeline. And we are going to understand the signal processing and activity modeling requirements. So how do we wear it? The first part is a wearable unit mounted on the hip. The second part is a wristband to be worn on your wrist. Interestingly, we designed this by considering correspondence of form factor and on-body location with the smartphones and smartwatches. The first part of our hardware is the ESP wristband, which contains a battery, ESP SoC PCB, and a 3D printed case. And the second part is the HMB wearable unit. It contains a battery, Hummingbird Pro, 3D printed case, Wi-Fi NFC, and two 60-degree conical horn directional antennas. Okay, we all understand that we need a battery to power our wearable, and we need a 3D printed case to hold that. And we need a processing board and a Wi-Fi NFC to collect radio signal. The why do we need direction antenna? The number is 2, and the coverage is 60 degrees. Let me explain. So we all understand that the activity of human body consists of different movement of different parts. For example, if you're running, you are swinging your both arms and both legs. And if you are brushing your teeth, the movement only involves the movement of your dominant hand. So we need directional antennas to cover different body parts in order to provide fine-grained information. We decided to go for 2 antennas, one pointing to the upper body, the other to the lower body. Now that we decided we go for 2 antennas, the interesting problem, the problem right now is what's the radiation coverage of the direction antenna. Here we list 3 scenarios. In the first scenario, the radiation coverage is too short, too narrow to capture the interesting part of the body, such as the arm movement in our case. And the second scenario, the radiation coverage is so wide that it's not only cover the interest of your body, but also covering the movement of the people nearby, introducing interference of the ambient environment. So we need to cover relevant body parts while excluding others, which is shown in the third scenario. We decided to go for 60 degrees by modeling the person body and the people distance with a social distance. In the third step, we use software to simulate antenna and design this antenna. What we use as a standard for radiation coverage is a half power beamwidth, which is 60 degree in our case. And the last step, we 3D printed the antenna. Our radio signal processing pipeline contains 4 main modules. The first module is CSI extraction and pre-processing. What we do here is noise removal and dimension reduction. After that, we feed the filter data into motion detection module where we decide the person is moving or not. If the person is not moving, we feed data into a third module called breathing monitoring, where we can get estimated breathing rate. If the person is moving, we then feed the data into the fourth module called activity recognition, where we can get recognized ADLs. Okay, what is CSI? Modern wireless device that supports 802.11 standards use OFDN in physical layer. OFDN divides channel into multiple subcarriers, each carrying fine-grained information called channel state information, shortened for CSI. We then do noise removal by applying low-pass filter because radio signal is very noisy. The purpose is to remove noise and outliers that are not caused by the targeted activities. Especially, we select 20 Hz as our cutoff frequency. And then we use principal component analysis on the subcarriers because CSI has 30 subcarriers in our case, and they are highly correlated. Especially, we select the first projection of CSI data in order to remove redundant information. Let's move on to the motion detection module. In motion detection, we do this by determining whether an individual is performing some activity or stationary within a segment of CSI. In the bottom two figures, we show the variance of upper body antenna and the lower body antenna CSI. You can see clearly from the figure that the variance caused by walking activity is much more than that of stationary status. And if the person is not moving, we move to the breath monitoring module, where we do power spectrum density-based breathing estimation. We achieve this by applying PSD to first PC of CSI data in order to find frequency that contains the most power. In the left figure, we show the first PC of the CSI measurement when the user is stationary. We can see clearly from the figure that the person is breathing normally with the interval of one breath at approximately 5 seconds. After we apply PSD to the time series, we can find estimated breathing rate by looking at the peak power density, which is about approximately 0.2 Hz, and it corresponds to the 5 seconds in the left figure. And then, if the person is moving, we use empirical cumulative distributive function, feature extraction, and classification by applying the following formula. The purpose is to extract the shape information of a cumulative function of CSI amplitude time series. We use SVM to get the probability of each class of upper and lower body antenna. We chose this because it is lightweight, which is suitable for resource-constrained platform. Now that we get probability of upper and lower body antenna of each class, we then do multi-antenna fusion. We do this by using variance as a sensitivity indicator so as to fuse the upper body and lower body antenna. And it is because higher radio signal variance indicates more movement involved. For evaluation, we're going to evaluate an impact of different factors on our system, and we selected most representative results to share with you. We use NewLog respiration logger to provide breath data ground truth. For data collection, in the lab setting, we invited 7 subjects to provide script data, and in the real-world setting, 4 subjects are invited to help with unscripted activities. A total of 200 minutes and 2,000 minutes data are contributed for script data and unscript data, respectively. For the first experiment, we examine user-independent model for activity recognition. The user is invited to perform 5 ADLs: brushing teeth, shaking hands, typing keyboard, walking, and interacting with phones. We select this because it involves upper and lower body activity. We do leave one subject cross-validation, and the average accuracy is 72%. When taking a closer look, we can see that there is a large difference between highest and lowest level of accuracy. This is because subjects perform activity very differently, and a personalized model might be needed to improve accuracy. For the second one, we evaluate the performance of breathing rate estimation. We evaluate it by comparing to professional breath monitor. You can see from the figure that the average accuracy despite subject 7 is relatively good, is 97%, and the accuracy of subject itself is 78%. This is because the preliminary results show that body scan is overall reliable, but it can fail if the antenna is pointing to our wrong direction. And for the third evaluation, we verify the antenna design choice by comparing 5 antenna configuration. We benchmark using the same 5 ADL datasets, and we can see from the table that the upper and lower body antenna configuration has the highest accuracy, which is the design choice of our system. Let's take one example of a bad example. So in the bottom column, we apply an omnidirectional antenna and put on the same location as body scan, and it only achieves 50%, which is much lower than 78% of our configuration. And then we study the impact of number of people nearby. We operated body scan when there is 0, 1, and 2 people nearby the subject. We can see from the figure, especially in walking column, the recognition rate does not drop significantly across 3 cases. This is because we use direct antenna design. And these preliminary results show that body scan is robust to interference caused by nearby people. We also study the performance in the real world. We deploy the body scan in various locations such as meeting rooms, bedrooms, bathroom and parking lot, and we can see from the table the average accuracy is 60% across 8 activities, and it is worse than that of lab setting. And we think it is because real world is challenging. So body scan is a proof of concept regarding real world operations. In this work, we have presented body scan, a wearable system that uses radio as a single sensing modality to provide a unified solutions for activity and vital sign monitoring in a contactless and privacy-preserving manner. We also have demonstrated that the feasibility by evaluating body scan in both laboratory and real-world environment. And now, every mobile and wearable device has a radio capability, such as smartwatch, glass, smartphones, and wristbands. And we believe that body scan-inspired approach will open up powerful new applications of radio sensing on wearables, such as human-computer interaction, mobile health, and driving safety. Thank you. My name is Bi Fang. Happy to take questions.